Alright, here's a video for the last part of limits. It's limits at infinity, where x is unbounded. So the meaning of that is x is unbounded. It means as x increases without bound, what happens to y? Like if you had a graph like this, right, as x increases or goes towards infinity, or you could be asked about this way, and the graphs don't have to look like this, but this would be as x approaches negative infinity. So these are called limits at infinity, and the notation is going to look like this. Limit as x approaches infinity of some function, or perhaps the limit as x approaches negative infinity of some function. I tried to make a bunch of preload this thing so I wouldn't have to talk too much. Alright, so we're trying to figure out what y value, aka f of x, so also known as, we're trying to figure out what y value a function approaches as x approaches either positive or negative infinity, meaning as x increases or decreases without bound, what y value does the function approach? You can pause this thing if you need to read that again or whatever. An example. I'm trying to give you concept and analysis and computation throughout this whole video. So an example, I don't know why that's going so slow. The limit as x approaches infinity of the quotient 3 over x divided by 2. Analysis means what happens to the y value as x gets increasingly larger without bound. Right? That's another way to look at that limit. So in purple down there, here's what's happening number sense wise. As x gets larger, so does the denominator. The numerator remains fixed, it's always 3. So the resulting quotient, which is the ratio of the numerator to denominator, the resulting quotient gets increasingly smaller, but will always remain positive in this scenario. So the limit of this is 0. As this x value gets bigger, so does the denominator. So you have 3 over an increasingly bigger number, which means 3 divided by some really big number is some really small number, which means 0. It's going to get closer and closer to 0. Alright? Alright. I think I did. Oh, that's my phone. Hold on, let me get that. Just kidding, I forwarded that. Alright. Numerical analysis for that same limit is, that screen thing's being so slow. Looks like that. So as the x value in that diagram right there, as the x value, this guy, gets increasingly bigger, so this is getting bigger, you can see that when I plug in like 1, when I plug 1 into that x, I get 3 over 3 ultimately, which is 1. When I put 10 into that x, I'm going to get 3 over 10 plus 2, which is 12, so 3/12 is 1/4, which is 0.25. When I put in 100, I get 3 over 102, which is 0.03. And you can see, come on, you can see that this value, this is the limit, this is the y value, this thing's getting smaller and smaller and smaller, so it's approaching 0. So the limit of that thing is 0. So we showed you an analysis, what I want you to think of as the denominator gets really big and the numerator is fixed. The quotient is going to become increasingly smaller and approaching 0, and numerically here in this picture as well. Alright, what's next? Come on, screen shade. Oh, I didn't want that to move. Okay, this limit is still like whoever that was. Alright, the algebraic summary. This is getting kind of to the end here. move that back up. I don't know why there's a delay in that thing. Sorry. Okay. Got it. Give it a limit in the form of the limit as x approaches infinity. This little thing is not here. Of some polynomial divided by a polynomial. So I've got x to the n over bx to the m. We've seen this before. Remember, it's like kind of the notation in the rational zero test. This thing. You've got a numerator of degree n and a denominator of degree m. There's three scenarios possible. The 2 degrees could equal each other, this guy. N could be less than m, aka the degree of the numerator is less than the denominator. Or n could be greater than the degree of the numerator is greater than the denominator. Algebraically, then there's a way to look at any sort of limit at infinity to figure out what the limit's going to be. And it's similar to what we did with asymptotes earlier in the year. So if the degrees are equal, if n equals m, I'm talking about this one right here, then the limit is the ratio of a to b, right? Of these guys, the ratio of a to b. If n is less than m, so the degree of the numerator is smaller than the degree of the denominator, then the limit is 0. And if n is greater than m, then the limit is either going to be positive or negative infinity. And also that is a limit that doesn't exist. So example, I'm getting rid of this thing. I've kind of got my little notes up there. For me again. It's Miss Mitchell. Oops. Okay. Examples for the first one. Call this one number 1 right here. The limit as x approaches infinity of that polynomial right there divided by another polynomial or a rational expression is what I'm looking at. The ratio of the highest degree right there and the highest degree right there is equal. If those are equal, then the limit is the ratio of these two coefficients. It's 3/5. Or in this scenario over here, I could even have the limit as x approaches negative infinity. I'm just looking as x is getting going to the left without bound. I see again, that is the same as that. The degrees are the same, therefore 3/5 is the limit. You can graph that too if you want to look at that, like a picture of it. The second one, I've got the limit as x approaches infinity, same kind of thing, rational expression, and this time I'm comparing 2 to 3. So in this case, the numerator is smaller than the denominator, which is this scenario. Numerator is smaller than the denominator, which means the limit is 0. It's always going to happen. You can look at a graph. There's another way to show this, which I'll probably show us in class, but ultimately it's going to be 0. It doesn't matter in this second part if the limit's approaching negative infinity. The resulting limit is still 0. Sorry, if the x value is approaching negative infinity. And lastly, I've got number 3 here. If the degree, there's the 2 degrees, the numerator this time is bigger than the denominator, and in my little chart above, that means that this limit is infinity. Or in this scenario, if my x is approaching negative infinity, then I still have the the same, where the numerator degree is greater than the denominator degree. My limit is negative infinity. Or, different scenario, I just put a negative in front of this guy, but I kept everything else the same. And I have my x is approaching positive infinity. This time my limit is negative infinity. That should be enough info to help you through the Khan Academy anyway, and we'll continue to refine it during class.